Good morning, everyone. So we have come to the final day of our 5 days online FDP. On this day 5, we are starting with our first session, and this is the last technical session we have. And to culminate the event, we have with us the eminent speaker, Dr. Nagesh Kumar sir of IISC Bangalore. And sir is exponent in soft computing technique. So this is a wonderful opportunity for us to hear from sir. I would invite Pratik to give a brief introduction of our speaker today.
Good morning, everyone. Today, our eminent speaker, Dr. Nagesh Kumar, received his PhD degree from Department of Civil Engineering from Indian Institute of Science, Bangalore in 1992. He has been a professor with the Department of Civil Engineering, IISC Bangalore since May 2002. Earlier, he was with the IIT Kharagpur, India from 1994 to 2002 and National Remote Sensing Center, Hyderabad from 1992 to 1994. He was a Boy Scout Fellow with the Utah Water Resource Laboratory, Utah State University, Logan, UT, USA in 1999 and visiting professor in EMSC, Saint Etienne, France in 2012. His research interest includes climate hydrology, climate change, water resource system, ANN, evolutionary algorithm, fuzzy logic, MCDM, and remote sensing and GIS application in water resource engineering. He has supervised 10 postdocs and 20 PhD candidates. He is the co-author of 8 textbooks and published more than 210 papers, including 125 papers in peer-reviewed journal. He is the editor-in-chief of Journal of Water and Climate Change IWA Publishing UK and associate editor for ASCE Journal of Hydrologic Engineering. He is the recipient of IBM Faculty Award for the outstanding contribution in modeling hydrologic extremes using microwave remote sensing. It is our privilege to have Sir with us. Now, I would like to request Dr. Nagesh Kumar Sir to address the session and enlighten us with the knowledge.
Thank you. Thank you very much, Pratik. And I also thank Dr. Vipin for inviting me to give a talk in this FTP. It is really good that he could collect a good number of people as resource persons for this FTP. I went through the schedule and I'm really impressed at the way maybe I'm the last but not. So what we will do is, I'm from the schedule. Pratik or one of you can you please confirm that it is visible to you? Visible? Yeah, but my PPT. Okay, 1 second. Wonderful. Thank you. Right. So what we will do, I had noticed that on Wednesday you had two sessions, one on particle swarm optimization and one on genetic algorithms also. So what I thought is that we try to briefly talk about both of them and we try to somehow merge them together to have a much better hybrid algorithm. Okay, and then we try to use that for multi-objective optimization in various domains, and specifically I'll be talking about multi-object optimization in reservoir operation. So the whole idea is that to discuss about a kind of a hybrid algorithm which we have developed some time back using principles of particle swarm optimization as well as some of the aspects that we deal with in genetic algorithm and combine them together to have the advantage of both the domains. So To start this presentation or to discuss about what I am doing today, I must acknowledge one of my former PhD student, Dr. M. Jangareddy. He is now working as professor in IIT Bombay, and his PhD work, a portion of his PhD work, is what I am presenting today. So, with due acknowledgements to him, let me start my presentation today. So first of all, we'll briefly discuss about swarm intelligence. It may be kind of a recap of what you have already learned and see some of the principles of swarm intelligence in general and specifically about particle swarm optimization and how it can improve when we want to deal with nonlinear optimization. Once we get an idea about it, I'll also try to demonstrate it briefly, but then I will talk about a hybrid algorithm, which we call it as elitist mutated particle swarm optimization, which has some components of GA as well as PSO included in it. And we'll try to demonstrate how that can be solved to some of the textbook kind of problems and what is the efficacy while we are solving that problem. And then we will discuss about multi-objective optimization. And once we are comfortable with that, then again, I'll try to discuss about a hybrid algorithm that we have developed, and that we will discuss briefly. And we'll also compare with industry benchmark multi-objective optimization algorithm, NSGA. So NSGA2 versus our algorithm, we'll discuss it. And I'm trying to say which is better or which is great or something. That's not my idea. My idea is that this proposed technique can solve some of the nonlinear optimization problems as efficiently as many other optimization, multi-objective optimization algorithms that may be available in literature. More importantly, we'll deal with solving a problem in the domain of water resources, especially for reservoir operation. And before that, since some of you may not be comfortable with this, what I will do is I will also introduce why and how we deal with multi-objective optimization. At the end, we'll discuss briefly about the conclusions and future scope. And that's the way it goes. And I wish to mention that all my slides are numbered. So if you have any questions with reference to any particular slide, you can refer to that and put the text message on the screen. So and with reference to a particular slide, the actual way in which we are doing, what we will do is we will postpone this discussion to the end of the session so that there won't be any interruptions during the presentation. Now, the overall overarching domain of optimization itself. If you look at different optimization methods that are available, this is one way of categorizing them. This is not the only way, but this is one way of categorizing them, where we can talk about combinatorial optimization or continuous optimization. Combinatorial optimization can also fall under discrete optimization. Now, if we talk about combinatorial Ransom bound algorithm, dynamic programming algorithm, etc., which have been traditionally there for a long time. What you see in yellow boxes are the algorithms that are there for a long time, and we now refer to them as traditional algorithms. And compared to that, under combinatorial optimization, we have approximate methods, and we'll discuss about various approximate methods briefly. And one of them is what we are going to discuss in detail. Then if we talk about the continuous optimization methods, we have nonlinear as well as the linear optimization techniques. And within linear, we have linear programming, and that can be solved using different algorithms. One of the most popular is simplex method. We can also talk about its variants like revised simplex method, etc. And if you want to talk about some advancements for large-scale linear programming problems, we also have what are known as interior point search algorithms, and also Karmakar's algorithm proposed by our own Indian while he was working in IBM. So that's also very powerful search algorithm. But all these algorithms basically work only if the problem, optimization problem itself, is linear. If it is non-linear, it cannot solve. Then for non-linear, we have two broad categories again, a global search method as well as local search method. When you talk about local search method, we have gradient based as well as without gradient based approaches, Lagrangian multipliers, optimization with calculus, all those things will fall under this category. They can also result in global optimum if the function that we are dealing with and the problem domain that we are dealing with is either convex or concave. Otherwise, there is no guarantee that we get global optimum. And other global search methods include, that can also be taught as combinatorial approximate methods. So we have heuristic methods, meta-heuristic methods, and random search methods. And today we'll be discussing about meta-heuristic methods. And within meta-heuristic again, we have single solution based search. That means every time we'll be searching for one solution, or population based search, where we'll be searching for multiple solutions every time. And among them, one of them may be the best solution. So if you talk about single solution based search methods, we have simulated annealing, taboo search, etc. And they have been very popular and they are also used very often. But when compared to them, more often used approaches are population based search algorithms. Within that, again, if you want to divide, we can talk about evolutionary algorithms and also swarm intelligence based algorithms. Under each category, if you want to talk about evolutionary algorithms, we have genetic algorithms, differential evolution, evolutionary strategies, evolutionary programming, shuffled complex evolution programming, so on and so forth. And if you talk about swarm intelligence based techniques, we have particle swarm optimization, which we are going to focus today, and ant colony optimization, honeybee mating optimization, a firefly algorithm, shuffled frog hopping algorithm, looping algorithm, leaping algorithm, cuckoo search, J algorithm, and many other things. So what we will deal with today is that we want to use the swarm intelligence based optimization, that is particle swarm optimization, and some of the principles of evolutionary algorithm, specifically genetic algorithm, and we want to use the advantage of both of them in a hybrid algorithm to improve the efficacy of particle swarm optimization. So that's what we are going to deal with. And what is important? It's a population-based search. Means for every generation, for every iteration, what happens is we don't deal with one solution, we deal with a set of solutions. That depends on the number of members in the population or number of particles in the swarm optimization. So that is a very interesting aspect which I am going to deal with when I want to deal with multi-objective optimization. So please note that point. At any stage, when we are doing any iterations or generations, what we are doing is we are dealing with a bunch of solutions. And among them, one of them may be the best, depending on how you rank them and other things based on objective function value. So that's what we are going to deal with. So today we are dealing with, within this entire domain, GA and PSO. Somehow we try to use the advantage of both and get the best out of both the worlds. Okay. And this work that I'm quoting this figure and other things, we have recently published a state-of-the-art review paper on various swarm intelligence and evolutionary algorithms available in the literature, and what are the advantages versus what are the disadvantages, what is the typical flowchart or pseudocode to implement them, and then how they are applied in various domains of water resource engineering for optimization as well as for search. Okay. So that's done through this particular paper. At the end of this presentation, I will give you the complete reference for this paper. And I can also share this with Dr. Vipin so that he can give it to all of you. It's an open access paper. And let me warn you, it's a very long paper. It's about 52 pages in a printed volume. So you can imagine it's almost like a textbook. So you can also see that. Okay. But what we'll do now, first of all, we'll talk about swarm intelligence. The swarm intelligence, as the name suggests, we have group like a swarm, and that group's intelligence is what we want to utilize. There could be, like, for example, there are so many honeybees here, okay, and how do they do, in terms of nest building or in terms of getting the honey to their nest or any other aspects? How do they do the optimization, and how do they talk about their production, honeybee mating and other things? Okay. Okay, that's swarm intelligence. In the same way, if you talk about ants, okay, ANTS is an acronym standing for Ant System. Okay, and that will talk about how ants communicate with each other. They don't talk to each other, but they still communicate through one chemical called pheromone. And the pheromone deposition concentration is the one that is used. And the point there is ants are well known, are very famous for finding shortest path between the source and the sink, or basically between the food and the nest. Okay, and how do they do that? And what is that we can do to use their intelligence to solve some of our optimization problems, like, for example, critical path method or PERT, or even for that matter, if you want to find out what is the shortest pipe length that we should put from the source of water to the city or the locality where we are supplying water. So water distribution network optimization, many things can be done through ants. The same way, I mean, all of them can be used by any swarm intelligence technique. Now, another interesting concept, of course, we can discuss about each one of them like this, but another interesting concept that I want to talk to you about these birds. I hope you can see the birds in this way. Okay? And these birds are very popular in the sense that they migrate from one continent to another continent. Okay, something like from Africa, some birds will come to a place near Bangalore called um, near one place in near Bangalore. Okay, and there they will spend their summer here because weather is good here, and then they'll go back that distance. So they fly that long without much difficulty. Nowadays, if you want to talk about intercontinental travel, like flying from here to etc., typically you have to stop somewhere for refueling, right? Even the aircraft has to stop for refueling. Whereas these birds are so efficient that they travel so long without much difficulty. And how are they doing? There is a very interesting concept here. You can see these birds are not in one straight line. They are actually in the form of one very interesting shape, which is referred to in aerospace engineering as aerofoil. Okay, so what happens is if a bird, the first bird that is moving in this direction, okay, when it flutters its wings, it will create some turbulence. And that turbulence, if there is a bird just behind it, okay, then what happens is the bird will have to use more amount of force on its wings to travel at the same speed because of the turbulence created by the bird that is going ahead of it. But instead, if it is not just behind it, but it is slightly behind in a left or right to the original bird, then what happens is it can utilize the turbulence that is created by the leading bird, and therefore with less amount of energy it will be able to travel at the same speed as the first bird. But in the process, what happens? These birds which are in the backside, they will be using less amount of energy, and the first bird will be using more amount of energy. So it may get tired. At some stage, the leading bird will be replaced by some other bird. That's where they try to utilize their swarm intelligence or group intelligence. Okay, and the bird also should find the direction which it should go and at what velocity it should go. Okay, so if we now treat all these birds as like particles, okay, that's where we talk about particle swarm intelligence. Okay, so we will deal with particle swarm intelligence in today's talk first. Now, if we talk about swarm optimization in general, some of the major principles based on which swarm optimization takes place, they are specified here. I'm quoting this paper. Okay, so swarm should be able to do simple space and time computations. Okay, and that is proximity. And swarm should be able to respond to quality factors in the environment, such as the quality of food or safety of location. So it should also be concerned about the quality. If it should not suddenly encounter very rough weather or rough environment in terms of heat, cloudiness, or turbulence, jet propulsion, anything. Okay, so it should be able to deal with it. And swarm should not allocate all of its resources along excessively narrow channels, which is not good in the sense that it may end up in local optimum but not global optimum. Okay, and therefore it should distribute resources into many nodes. That is called principle of diverse response. And these two are last two are slightly contradicting, but both have to be ensured. Swarm should not change its mode of behavior upon every fluctuation of the environment. That talks about principle of stability. At the same time, swarm must be able to change behavior mode when it matters. Principle of adaptability. So these two are actually kind of contradicting, and we try to ensure both of them happen and in any swarm intelligence based technique. So these are the five or six major principles that will be used to develop any swarm optimization algorithm, including the one that we are dealing with today, particle swarm optimization. Now, if we talk about particle swarm optimization, first of all, it's generally considered as a model for socio or social information sharing, like the way birds share their information. Okay, so that's what we have to ensure as far as particle swarm optimization is concerned. Now, what are the ingredients here? First of all, a particle consists of what is its current position, okay, where it is right now, the velocity at which that particle should move, and then pk is the position of that particle, right? So these three plus what is the way we are trying to update the velocity as well as the position are the important parameters or important attributes that we put to PSO to go ahead and solve iteration after iteration. So what we are doing from every iteration is for every particle we are changing its position, and we are also deciding the velocity at which that position should be attained or reached. Okay, so while we are doing that, that means what we are doing here, moving particles in the set space, which refine their knowledge by interaction with their neighbors. It is not only moving in its own best path, but what is also doing is it is interacting with other particles. That's where the social information sharing comes into picture. So what is the advantage here? We have both worlds. It combines private knowledge, that is best solution each particle has found, public knowledge, best solution entire group has found. So every iteration, these two will be utilized to talk about velocity or particle position update. Okay, and at the end, we are supposed to reach global optimum and perhaps mini suboptima. I want to stress upon this point more in detail. When we obtain the optimum solution, even at that time, if we have started with about 20 particles, all the 20 particles will be there in the last iteration also. And one of the particle may be showing the best solution. But what happened to other particles? Those particles are showing solutions which are very close to the optimum, but may not be the best. They are also very good, but they are not the best. Okay, and that concept is very, very useful when we want to talk about multi-objective optimization. So I will deal with it again when we talk about multi-objective optimization. If you want, I mean, this is the only slide where I will show you a couple of equations as far as the algorithm is concerned. Then I will only talk about applications. Okay. So if you want to talk about velocity, as I said, velocity and position need to be updated. Now, velocity of the particle is updated by using three different components. I don't read this equation, but I'll just try to summarize what are these three components. Okay, the part that is in here is called inertial part. What is doing whatever the direction it has been moving so far. Okay, it tries to maintain that inertia. So therefore, it tries to maintain same direction or very close to that direction. So that is what is done by this component as far as velocity update is concerned. The next component is with respect to its private best. That means that particle, whatever the best it has found, around that we try to move the particle. So that velocity is decided based on the private best, which is referred to in particle swarm optimization as cognition part. And the last component here is actually social information sharing, that is the public best. Okay, turns towards the public best, that is the social part. So velocity updation is followed or is done using three components: inertial part, cognition part, and social part. Using these three and giving some due weightages for each of these points, and also giving the amount of transformation that we'll do by doing all these components together, the velocity of each particle is updated. Okay, so the parameters for PSO are already clear to you now. Okay, these weights and other things that we are going to decide. Now, once the velocity is updated using this rule, using this formula, or using this equation, then the position is updated using this updated velocity. Very simple. What are the time interval that we have chosen? Over the time interval, the velocity is multiplied so that you know the distance to be traveled, and the distance is what the new position for the path. If I am from the current position, it has to go to this new velocity action updated using these simple rules. Now, the advantage is, there are three components here: inertial part, cognition part, and social part. Because of these three components, which are also implicitly there here, okay, then what happens is we are trying to talk about the balance of exploration as well as exploitation. Okay, so both can happen. I mean, one is private and another is public. Okay, so both can happen, and that's why the PSO seems to have a very good advantage when compared to the traditional nonlinear optimization algorithms. Now, what we did is that to that PSO or to that particle swarm optimization, we slightly tweaked it. What we did is that, in genetic algorithm, you would have had something like mutation, and you would have had something like elitist members. What happens in case of genetic algorithm? Elite members will be retained from the current generation to the next generation without any modification. They are called elite members, right? And while after we perform crossover on the offsprings, and the mutation probability, we perform mutation. We try to modify the offspring. Right? So that aspect of alignment and mutation are being used here to update the particle swarm optimization itself. So that's the tweaking that we are doing. Okay. So how do we sorry, some the audio. Thank you. Hello. I'm sorry, somebody's audio is on. Dr. Vipin or somebody can control that. Okay. So what we'll do is, first of all, at any iteration, we sort all the particles, which we have to do even to find the private best, etc. We sort the particles and then try to put them in descending order. So the one that is at the highest has the best fitness in that current iteration. Now, those are allied particles, right? Like your GA. Then what we do is that we try to find the last particles which are in the descending order. They are the worst particles. So the worst particles in the current generation or current iteration is with elitist members. That means we take the allied members, the top members, we mutate them, and then use them to replace the worst particles. Therefore, you might be able to converge to the optimal solution much faster. This is a simple thing that we are doing, and that we call it as elitist mutated particle swarm optimization. So perform lattice mutation on a number of particles, which is, let's say, NM max. So pseudocode for that is very simple, like this. So what we are doing is, now we are trying to hybridize the PSO with GA concepts. The two GA concepts that we use here are allied members and mutation operator. Okay, so those two are used here to replace the worst particles with the elitist mutated particles. Okay, that's a tweak that we are doing, and let's see its effect. Now, if you want to talk about the entire EM PSO, That's the new algorithm that we are talking about. Lattice mutated particle swarm algorithm or particle swarm optimization algorithm. Okay. Initial portion is same, generate initial swarm position and generate initial velocities and decide the number of particles, etc. Okay. And until the stopping criterion is met, okay, complete fitness function for each individual of the swarm. Update P best and G best, particle best and global best. Okay. And perform PSO operations. Okay. That is velocity updation and position updation. Then after that, we sort the members. Up to this point, it is simply SO itself. But this is the place we are tweaking. What we are doing here now, we are performing latest mutation. And that is the next generation. And keep on doing it, or next iteration, and keep on doing it until termination criterion is satisfied. That's EM PSO algorithm. Now let us try to apply that for some simple classroom kind of problems to start with, and then for large scale problems. This is a very simple classroom kind of problem which is used in mathematics very often. And if you notice this function z equal to x exponential of minus x square minus y square. Okay, so as you can notice, it's a highly nonlinear function, and it's very difficult to find its derivatives and solve it using any Lagrangian approach or something like that. And even if you want to search any such techniques also, if you look at the domain within the range of x taking minus 2 to plus 2 and y taking minus 2 to, let's say, plus 3, this is a range. Okay, and within that range, if you substitute any possible value of x and y, z will get some value. Okay, and what we want to do, we want to find out where or which combination of x and y z is maximum. Okay, and if you can see these contours that are shown here, okay, and you see the color legend also here, what you can notice is that this point is the point where this function will have the least value, and this point is the place where the function has the highest value, maximum value. So our optimization approach is in such a way that finally the solution should be found here. Okay, it is very clearly visible through graphical depiction. Now what we will do at iteration 0, we randomly put the particles, maybe uniformly distributed over the entire such domain. Such domain is minus 2 to plus 2 as far as x is concerned, and minus 2 to plus 3 as far as y is concerned. In this domain, the symbols that you are seeing here, these are the particles that are there in this domain everywhere. Okay, and as you can notice that this is the place where, as you keep on driving, searching, you will be hitting towards minimum. We don't want that. We want maximum. So what happens is, as you can see, by the time we reach iteration 10, okay, none of the particles are in this place. All the particles are number of particles are same. Please note that. Okay, but all the particles have now moved here because the maximum is somewhere here. So by iteration 10 itself, all the particles have moved to this domain where maximum is there. And by about iteration 20, okay, some particles have already hit here, are very close to this place, and they are very close to this lower contour where it's like a hill peak. Okay, now by the time we reach about iteration 30, okay, you can notice that most of the particles are at the optimum, are very close to the optimum. So in about 30 iterations to solve this problem, we have hit the global maximum. Okay, now that's a simple classroom problem. We can solve it using PSO or EM-PSO. You would have got it in almost the same time, not a big difference. But if you are trying to solve much large-scale problems, okay, and this is one problem that is beaten around substantially by any person who develops any new algorithm. First of all, they try to, in the field of water resources, first of all, they try to solve this problem. This problem is actually proposed by Larson way back in 1968, when he has proposed a new algorithm based on dynamic programming. He wanted to test that algorithm using this particular problem and solve it and see whether it is more efficient than the traditional dynamic programming. Okay, successive approximation method. Okay, but what is done, this is a very simple problem. It's actually almost like a hypothetical or classroom kind of problem again. What you are seeing is there's a multi-reservoir system. Okay, there is a reservoir here with a powerhouse to generate hydropower. There is a reservoir here, powerhouse, reservoir here, powerhouse, and reservoir here, powerhouse. So 4 reservoir system, and you can notice that this reservoir and this reservoir are in parallel. Okay, that means this is for one tributary and this is on one tributary, and both are joining here. And this reservoir gets inflows from this system as well as from this system. So these two reservoirs in series, and this reservoir and with these two reservoirs are also in series. Okay, and all these reservoirs, this for reservoir 1, 2, 3 are only for hydropower generation, whereas this reservoir is not only for hydropower generation, but it is also for irrigation. It supplies water. Okay, so the objective function is basically to maximize the benefits that we get by releasing water for hydropower as well as for irrigation. Okay, so the first portion that you are seeing here, there are 4 reservoirs, therefore 4 powerhouses. Okay, so what you are seeing is this RRT talks about the release that is made from the reservoir in time period T from reservoir number R. It may be 1, 2, 3 or 4. So R is ranging from 1 to 4. And the release that is made from the reservoir 1, let us say in period 2, okay, it may have some associated benefit, and that benefit coefficient is which will change for every reservoir, also for every time. Okay, so let us say that we have 12 time periods, that is 12 months. Okay, so what we are doing, the benefit that we are getting from each reservoir in one time period, that is added over all the 4 reservoirs, then added over all time periods. Okay, that's the total benefit that we are getting by releasing water for hydropower over the year from this 4 reservoir system. In addition, this portion is actually talking about the irrigation benefit, that is from the reservoir 4 when we are releasing some water in a time period. Okay, and the corresponding benefit that we get, okay, to distinguish we call it B5T because B4T is power benefit. Okay, so here this is actually again summed over all time periods. So that talks about the benefit that we get from irrigation, and this sum is what we are trying to maximize. Objective function. Okay, system dynamics are continuity equations, like storage in any reservoir at the end of the time period should be equal to storage at the beginning of the time period plus inflow minus release that is made. If you talk about reservoir 1, release is only made for hydropower, and if you talk about reservoir 2, release is only made for hydropower. But if you talk about reservoir 3, what happens is the water that is released for hydropower or any releases that are made from the reservoir into the river will come as inflows into this reservoir. So that has to be accounted. So releases that are made here are included as inflows here. Okay, and then if you talk about the 4th reservoir, what happens is apart from the release that we are getting from here, and any intermediate catchment flow plus these things are added, and then only the release that we have to talk about, this R4T, will be for power generation. You can also talk about hydropower generation and irrigation generation if you want. Okay, so that's the way we can deal with it. And then we can also deal with storage lower limits, what is the minimum capacity to be maintained, and storage upper limits, what is the maximum capacity to be maintained. And then in each time period, what should be the initial storage and what should be the final storage. I mean, not for every time period, but for all time periods, beginning of the year and end of the year. Based on that, we also talk about release bounds, storage bounds, etc. All these things will become constraints, and these constraints are to be dealt with in particle swarm optimization. This is a traditional problem. It has been solved for many number of years using many number of approaches. So I'll just give you a summary of it. This problem is so nicely formulated that if you want, you can as well solve it using linear programming method. That means you will definitely get the global optimum using that. So what we are trying to aim at is that using any of these approaches, okay, we are trying to get that solution or not. Now, if you look at Larson in 1968, when he proposed this algorithm, DPSA, which is called Dynamic Programming Successive Approximation, Okay, he got the best value 401.3, and that is actually the global best solution. Okay, then 1971, a big another variant, discrete differential dynamic program was proposed, and that also got the similar solution. And in 2003, one of my PhD students in IIT Kharagpur, he has proposed an algorithm called FDP, or folded dynamic programming, and we also got solution very close to the optimum. And now in today's presentation, what I'll show you is that we try to use PSO, particle system optimization. We also use genetic algorithm, and we use optimization. Time can be measured on computational time, but which is subject to which computer you are using. Instead, one more way of talking about is flops, that's floating point operations, or number of function evaluations taken to solve the problem. So if you talk about it, PSO has taken about 748,000 and GA has taken about 2,279,000, sorry, 2,279,500. And if you talk about EMPSO, it has taken only 325,400, which is the least amount of computational time that this algorithm has taken when compared to others. All of them hit the solution, but the speed at which they have hit the solution is important here. And to do that, what we also do now, maybe it's doing once properly, but other time it may not do well. So what we did is that we try to do it with various initial sets of population or particles, okay, and try to find out what is the mean fitness. And here you can also notice that mean fitness is also very high as far as UMPSO is concerned, very close to the optimal. And number of function evaluations taken over on an average also is much lower when compared to other algorithms. That's when we develop the confidence that, well, this algorithm seems to be doing well. That's as far as EMPSO is concerned. The next aspect that we will deal with now is to deal with multi-objective optimization. In case if you already know, it is fine. Actually, it is as simple as, if you have a certain amount of money that you have received as salary on the first of a month, okay, then you have to deal with multi-objective optimization, right? You have to decide how much money, let us say, you will get your wife or a partner, and you will spend how much money for, let us say, entertainment, how much money for food, and how much money for saving, and things of that kind. So there you will be doing multi-objective optimization, because if you want to optimize how much amount of entertainment that you get, you may have to compromise on some other expenditure. Or if you want to spend all the money on eating nice food by going to good joints, etc., which Gujarat is very famous as far as a lot of food is concerned, then what happens? You may have to compromise on maybe saving that much money. Okay. So you have multi-objective optimization happening in our life every day in every aspect. Okay. But the problem here is the way that I have just explained to you. The issue is that we have the same amount of resource, maybe the amount of money in your wallet, okay? And that resource, how do we want to optimally utilize? And there is no one single solution here. The definition of optimization itself will be different. Our objective function itself could be different. Example, if my objective function, just to illustrate that point again, is just to eat well, then what happens? I'll be spending all the money for eating. And in the process, I may be compromising heavily on other possible or potential objectives that I may have. That talks about objectives conflicting with each other. If these objectives are not conflicting with each other, we can deal with them as if we are doing single objective optimization itself. But because there is a conflict, there is scope for conflict because we are competing for the same resource, then we have to deal with multi-objective optimization. And this is the point I will touch upon for about next 10 minutes to drive that point home. And I try to do that in the context of water resource systems. Okay, if you want to talk about water resource systems, okay, there is a good chance that we may have conflicting objectives or goals. For example, if this is a reservoir,
ध्यान नहीं रहता है, अपने कवर लगा के घूम रहे हो, साथ नहीं लिए थे ना अभी मोबाइल ये या अलग.
thank you. So whenever there is audio interruption, I will pause like this. Okay. So you can notice that there is a reservoir, and the reservoir is having so much of water. This is a water resource that is available to us. Now, how do we want to utilize this water source? There are so many possibilities. You may want to utilize that water, let us say, for irrigation, or you may want to utilize that water for hydropower generation, or you may want to utilize that water for drinking water supply or industrial water supply, or you may want to keep that water without using, so that that water will be available for the next time period or next time period, and so on. So there are so many possible ways in which you want to utilize this resource, and there is a scope for conflicting nature here. Okay, that is the one that we are talking about. For example, let us say for reservoir operation itself, one objective is, let us say, minimize flood risk. What do we mean by that? We want to keep the reservoir as empty as possible, so that when a flood comes, all the flood water will be accumulated in the reservoir, and there won't be any downstream damaging effect of that flood, because the flood is cushioned through the storage available in the dam. So what you are doing, you are trying to minimize the flood risk. But let us say that we have another objective which talks about maximize the hydropower generation. Then what happens? Hydropower generation is basically a function of two variables. One, what is the amount of water that is flowing through the turbine, and the next one, what is the head causing the flow, gamma QH, is it not? So it's a nonlinear function, of course. Then if you want to talk about that, for a given discharge, you can produce more power if you have more head available. More head available means what? The reservoir level should be very high. Reservoir level should be very high means what? Reservoir should be almost full. Okay. So if you want to talk about hydropower optimization, you want the reservoir to be at the highest level possible, so that if you release water per unit water, you get more amount of power because the head causing the flow is very high. Right? You can clearly see the conflict now. As far as flood is concerned, we want to empty the reservoir so that we can accommodate the flood. As far as hydropower is concerned, we want to keep the reservoir at the full level so that we can produce maximum amount of hydropower. Right? There is a conflict, which is good. Again, it depends on what is the importance that you give to these two objectives, which is of more higher priority to you. Based on that, we can talk about multi-objective optimization. And that's just two objectives. But let us now add more stuff to it. For example, let us say that we want to talk about minimizing irrigation deficits. What happens in every period, we have some irrigation demand. You supply water in such a way that the water supplied is as close to the demand that we have as far as irrigation requirement is concerned. That means the crops or the agricultural crop will grow at its best because all the water that is required is supplied, and therefore you are expected to get the maximum yield. So what does it talk about? Again, it talks about releasing water from the dam and supplying that water for irrigation to ensure that the irrigation deficits are minimized over a period of time. Again, it's conflicting because hydropower says that you should keep the reservoir at full level, whereas irrigation demand says that you should release that water for irrigation. Right? Then talk about one more objective. Let us say that because we are blocking all the water by constructing a dam, there may not be sufficient water flowing downstream of that dam in the river. And if there is not sufficient water, what happens is water quality will suffer. And because of that, the flora and fauna will be affected downstream of the dam in the river course, to such an extent that they may vanish. So you want to maintain some water quality in the river, and that are the flows that we release from the dam to maintain that minimum water quality in the river, so that all the pollutants that are there can be diluted to the sufficient extent, and that water that we release from the dam may not have any other purpose, okay, but that water that we release from the dam may be very much required as far as water quality downstream is concerned, and those flows are called environmental flows that are released from the dam. Okay, so again, that is conflicting with either irrigation demands or hydropower. Of course, it will not conflict as far as flood risk is concerned because you're emptying the reservoir, or you're emptying the reservoir to that extent. Okay, so you have objectives. Just now I listed about 4 objectives. Okay, and these 4 objectives themselves are highly conflicting or competing with each other, and many of these objectives may also be nonlinear. So involves many variables which nonlinearly affect all the features and the behavior of the system, and there are also conflicting objectives or goals in the system. So that's the kind. I mean, I'm just giving you only 4. You can talk about many number of such objective functions. For example, drinking water requirement, industrial water requirement, and many other things. Okay, and this is for one time. And if you are talking about over the period, let's say 1 year or 10 years, then what happens? We have to also worry about how much water we should store for the future periods versus how much we should use in the current period itself. Okay, so all these things will come into picture when we want to deal with multi-objective optimization. So that's where we talk about multi-objective optimization. So finally, what we are doing here is, as you can notice, that if you have this kind of multiple objectives, we are not really dealing with a unique solution which can satisfy all these objectives to the highest extent possible. Not possible. What we are trying to do is that at least for one objective, we get its best value, and for other objectives, as much as possible, we try to get its best value. You got my point? So there is no unique solution here. Okay, one objective, we try to get its best value. For other objectives, we try to get as much best value as possible, so that the overall solution is a kind of a compromise solution. It is not the best. There is no global best here in multi-objective optimization. We are talking about some kind of compromise solution. So what is the best? For example, let us say that I want to give highest priority to hydropower generation. Then what happens? I'll try to maximize the amount of hydropower that I can produce. Okay, it gives me that. But at the same time, what I will do is that the flood risk minimization, I try to reach it as much as possible. And irrigation deficits, I try to make them as close to zero as possible. And water quality also, I try to maintain the required standards. Try to maintain the standards. Okay, but the highest preference is given to hydropower generation. That gives you one compromise solution. Other solution could be, let us say that I want to minimize the flood risk. That is my highest priority. Then what happens? We try to minimize the flood risk. That means we try to empty the reservoir, and we may not be able to produce that much hydropower, etc. But still, there is no risk as far as flood is concerned. Okay, and then what happens? Flood risk is minimized, but the amount of hydropower produced then will not be equivalent to the hydropower that you would have produced if you have given hydropower optimization as the highest priority. Okay, same thing happens with irrigation deficit, same thing happens with water quality. So you get another compromise solution. So we talk about so many such compromise solutions, and these solutions are referred to by one famous Italian economist. He's not a water resource guy, he's an economist. Okay, and he called, first of all, this kind of deriving multiple solutions with one objective being met to a great extent when compared to other objectives is referred to as Pareto optimal solution, named after him. We will discuss about it. But let me again mention this conflict of minimizing flood risk versus minimizing irrigation deficits, or minimizing hydropower generation, or maximizing hydropower generation. Okay, it is such a big issue that because of that, sometimes we have what are known as man-made floods. I think you know one situation where Surat itself suffered when there is a flood event that is taking place. Uh, Upstream of it, one dam is almost full, and they thought that water they can utilize for the next summer, so that the drinking water problems and irrigation requirements can be completely solved. So they kept the reservoir almost full. But then what happened? More amount of water started coming, more floods started coming. Then they had to suddenly start releasing water or flood waters from the dam. Flood waters from the dam, and there is already flood downstream in Surat. Okay, so these two further aggravated the situation, and it has resulted in a major flood event. Entire urban area in Surat was devastated. Like this, same thing happened in Chennai floods also. So many places in Kerala also it happened in recent Kerala floods. What happens is the risk versus conservative approach. That's a very serious problem in reservoir operation. Okay, the amount of risk that you are taking. Sometimes you may get large amount of benefits because you have taken risk, but you may also face the consequence because you may be able to, you may not be able to store that much water. Okay, so that talks about huge amount of conflict. Okay, so again coming back to this Italian Pareto. Okay, so what he suggested is very simple. Let me just show you with a simple example here. Let us say that F1 is talking about one objective function, that is minimizing irrigation deficit. Okay, and F2 is again talking about the minimizing flood risk. Okay, so let us say these are the two objectives that we have. Okay, then the optimal solution is that this should be minimum and this also should be minimum. Okay, both objectives we are trying to minimize. Okay, so the optimal solution should be very close to origin, and that is not possible because then you will not get any feasible solution. Okay, then if you look at the feasible solutions, if you look at this possible solution, this is feasible because the feasible domain is clearly shown in gray color here, means none of the constraints are violated as far as this space is concerned, or if you try to pick up any solution in this entire space, right? But within this, if you look at this solution, okay, this is an interesting solution, or if you're not seeing very clearly, if you look at this yellow dot here, okay, if you look at this solution, what you're seeing is that, neither F1 nor F2, for example, if you want to further reduce F1, what you should do, you should move slightly to the left. And if you want to reduce F2, you should move slightly towards down. Okay, if you want to either do either way, move this particle, okay, what happens is it will violate the constraints. So it is not feasible. Okay, so this is one such compromise solution which is giving relatively better values for function 1 and function 2, and it is a feasible solution. So that is what is referred here. A point X star belonging to feasible region is a Pareto optimal solution if there does not exist any feasible point X belonging to F such that X dominates X star. So this is a non-dominant solution. Okay, and that is what we want to arrive at. And interestingly, there is no one yellow dot here. There are so many yellow dots here, meaning this is also a non-dominant solution, Pareto optimal solution. This is also a Pareto optimal solution, and this is also a Pareto optimal solution. Let me explain the difference between these yellow dots. You look at this yellow dot. Okay, this yellow dot talks about the function 2, objective function 2 has the least possible value, right? But as far as function 1 is concerned, it has a very high value. Please remember, we want to minimize this function 1 also, but function 1 has very high value. You can notice this is 0 and this is highest value for function 1. Okay, so it has high value. Therefore, although it is a very good solution, what we are doing here is that we are giving more importance to flood risk when compared to irrigation deficit. Whereas if you look at this solution, what is happening here? The irrigation deficit is very close to minimum, but the flood risk is high. Okay, it is at this point. Okay, so these yellow dots are different Pareto optimal solutions, each giving some importance to one of the two objectives. And idea in any multi-objective optimization is to identify as many Pareto optimal points as possible. Okay. Now, initially when we started, what we would have done, we would have started everywhere, and then slowly all the particles or all the genetic algorithm members will slowly come into feasible region after a few iterations or a few generations. And within feasible region, they may be somewhere here, all the particles. Okay, these particles, okay, they will slowly. I mean, you can notice there are 6 particles here. Okay, and those particles will slowly move in such a way that after a few iterations or generations, okay, they will be hitting all these best compromise solutions. Best compromise is the English wrong word, okay, are compromise solutions, okay, or Pareto solutions, right? The whole idea in multi-objective optimization is to identify as many number of points, yellow points, as possible. Okay, so that is what we are trying to do. As far as multi-objective optimization is concerned. Okay. Now, what we try to do is how do we reach this? As you can see, these are all actually also on one curve, and that curve is called Pareto optimal front or Pareto optimal curve. If it is 2-dimensional, there is only 2 objectives, we call it as Pareto optimal curve. If it is more than 2 objectives, like 3 objectives or 4 objectives, okay, then we refer as Pareto optimal front. Our whole idea of multi-objective optimization is to talk about developing this Pareto optimal front using any multi-objective optimization algorithm. Okay, that's what we want to deal with. If you want to understand this concept again, I'll try to give you in a simple notation wise. Okay, a general multi-objective optimization problem can be formally defined as find the decision vector x. These are the decision variables x1, x2, etc. up to xn, which satisfies m inequality constraints and n equality constraints. Okay, up to this portion is the same as any optimization problem, single objective optimization problem. Okay, you have n number of decision variables, m number of inequality constraints, and p number of equality constraints. That is fine. But only difference is now, instead of having only one objective function, we have bunch of objective functions, f1 of x, f2 of x, etc. X itself is a vector. Okay, so we want to optimize multiple objective functions. Okay, that is what is the main difference. How do we do it? There are 2 ways in which we can deal with it. Any ideal solution, like Pareto optimal solution, okay, is to be found in such a way that this optimal point is within the feasible region, and it is non-compromising in the sense that it is giving the best value when compared to any other x as far as that solution is concerned, non-dominating solution. So we can achieve this, we can do this, and in this framework, we can solve any number of objective functions, not just 2, not just 3. And as a matter of fact, we can use the same approach even to solve a single objective optimization problem. Okay, of course, not the other way around. Any single objective optimization algorithm cannot be directly used to solve multi-objective optimization, but multi-objective optimization problems, algorithms can be used even to solve single objective optimization problem. What we are doing here is very simple. If you just deal with 2 variables and 2 objective functions, just 2 variables and 2 objective functions to start with. Okay, what we are doing here is x1 and x2. Okay, these are the 2 variables, and the gray portion that you are seeing here is a feasible domain. Within this feasible domain, okay, and we are looking at some solutions like P1, P2, P3. Okay, and that is as far as variable domain space is concerned. And same, and you can also now notice that P1 dominates, let's say, P2. Okay, and if we now look at the same thing, same plot in the objective function space F1 and F2. Okay, what we'll do, you take this P1 value, that is what is the corresponding x1 and x2, substitute in objective function 1, substitute in objective function 2. Okay, you get objective function value 1 and objective function value 2. You plot the point. In the same way, do it for P1, P2, and P3. You can see that these are the places where these solutions are there. And as you can clearly notice, when compared to this solution is better because we are trying to minimize. Okay, and this solution also may be better when compared to this solution. So this P2 is out. Okay, that is a way we can talk about developing the Pareto optimal curve or Pareto optimal front. I hope that is sufficient as far as multi-objective optimization is concerned. Now I'll talk about the advantages of using multi-objective evolutionary algorithms. There are many advantages. I'll talk about that. First of all, multi-objective evaluations. Why talk about multi-objective evolutionary algorithms at all? There are some advantages. In principle, MOAs deal simultaneously with multiple solutions. That is the case I have been telling you from the beginning. Every time in any generation, we have multiple solutions available to you. One of them is the best, but others are very close to the best. Okay, so that's one advantage. And that means we are talking about many number of points on the Pareto optimal front available in the last generation itself or last iteration itself. Okay, that's the beauty about multi-objective evolutionary algorithms. They can find several trade-off solutions in a single run of the algorithm instead of series of separate runs, as in the case of traditional mathematic programming techniques. Linear programming itself can be used to solve multi-objective optimization. Fuzzy linear programming can be used to solve multi-objective optimization problem. But every time we get one solution. So we keep on solving the problem, optimization problem again and again to get multiple trade-off solutions. That's not required as far as MOEAs are concerned. MOAs are less susceptible to structural forms of solutions, and which are a real concern for classical algorithms. Some of the structural forms are like, a given constraint or objective function, you want it to be, first of all, continuous. And other possibility is that you may want it to be either concave or convex, or the feasible region itself has to be convex or concave. Only then we can talk about doing multi-objective optimization using traditional algorithms. That is not a problem as far as MOEA is concerned. MOEAs attempt to find solutions to extremely complex as well as time-consuming, high-dimensional real-world applications that have multi-objective goals. I'll demonstrate with a couple of case studies. MOAs use little problem domain knowledge and can generate a good distribution of diverse trade-offs. That's a beautiful thing. We don't worry about continuity of a function, concavity of a function, and still we get very good trade-off solutions. MOA structures reflect implicit parallelism. Therefore, there is a scope that you can also do this on a parallel computing system like clusters or high performance computing, etc. You can do it even on that kind of system. There are a large number of MOAs developed over the past. Okay, I'm just giving a few of them, and in that the ones that are in red color are very popular, and the one that is specifically mentioned here, non-dominated sorting GA, NSGA1, NSGA2, and now NSGA3 is also available. Okay, so these developed in IIT Kanpur by Professor Kalyanmay Dev, who is a faculty in mechanical engineering department, for some solutions in mechanical engineering optimization. Okay, and those things are available. And now if you want, you can also download that algorithm software from there, which is called KANGAL, KANGAL, Kanpur Genetic Algorithm Laboratory. Okay, so from there you can download the software either in C, Fortran, or maybe in Python. Okay, so other strength Pareto evolution algorithm, which is actually based on Pareto optimization, and Pareto archived ES method, and this is also more or less based on swarm intelligence based approach. Okay, and the one that we propose in today's class, okay, that also we try to use. Okay, so what is the consideration as far as MOEAs are concerned? First of all, we have this Pareto optimal front, and we want to reach here. So we start with this particles somewhere outside or within the domain, solution domain, and then slowly they converge towards the optimum, and they will finally reach this front. Okay, and what we want to ensure that all of them, all the particles should not aim at only one solution, one trade-off solution. They should be diversified. They should be able to identify all of them. How do we do that? Okay, first of all, preserve non-dominated points. Let us say after about 20 iterations, it has found one solution here. We should not lose it. Okay, that is elitism. And progress towards points on optimal front. So it should slowly move towards as many points on this front as possible. Maintain diversity, which is very important. Otherwise, you will be getting only one compromise solution, which we don't want. Points on Pareto front, which is known as phenotype, and our Pareto optimal solutions, which are known as genotype. Okay, so provide decision maker a limited number of Pareto feasible solutions, Pareto optimal solutions. If you give too many, he will be confused. If you give too less, he will not have scope for decision making. Okay, so I try to give the required number of Pareto optimal points. Okay, how do we do that? There are many ways, elitist mutated or many other approaches that can be done. I have mentioned about already SPA, PAS, NSGA, etc. Okay, and then we also talk about our own technique. So slowly we want to converge towards this solution. While we are trying to do this, three aspects that are to be properly taken into account, which I already explained, but I will explain it again. Okay. First of all, convergence. How to guide the population towards the Pareto set, which is referred to as fitness assignment. Then how to maintain diverse Pareto set approximation, density estimation. We don't want all the points to be here. If the density is very high, we want to distribute. So make it less concentrated here. Okay. So density estimation, and based on that, try to diversify. Third one, how to prevent non-dominated solutions from being lost. If you have already reached a non-dominated solution, try to keep it. That is archiving. That is what is called archiving. So we try to keep that solution. How to prevent non-dominant solutions from being lost. So these are these are three important principles based on which we develop various multi-objective evolutionary algorithms. So the one that now I will be talking to you is what I have already talked to you briefly in single objective optimization. We will now extend it to multi-objective optimization. Elitist mutated multi-objective particle swarm optimization, EM, PSO. Okay, so it has the advantages of GA, it has the advantages of PSO, and it is actually doing multi-objective optimization. So basic components, PSO algorithm is there, and variable size external repository. This is a place we try to reserve or try to store those particles or those elements which have already hit the Pareto optimal front. Okay, and then crowding distance computation. If all the particles are very close to each other, they are at the best solution, but they are very close to each other. Compute the distance between them. And if the distance is very small, then avoid them. Try to take away some particles and throw them out. Okay, that is crowding distance computation, and which I already mentioned to elitist mutation. And we also want to handle overlapping solutions. So all these things are incorporated into this algorithm. Okay, and this algorithm itself is published in this journal and also many other papers which are available in my website. So now let us try to use this EM-MO-PSO for optimal reservoir operation for multi-objective optimization. I'll try to show this, illustrate this with one particular reservoir called Bhadra Reservoir in Krishna River Basin in Karnataka state. Okay, and this reservoir has multiple purposes, multiple objectives. It has a hydropower generation in a right bank canal. The power is generated from here and it goes to irrigated area. That water goes for irrigation. Okay, and in the same way, you have left bank canal, and there also hydropower is generated, and then it goes to irrigating left bank command. And in addition, at the river bed level, when compared to these two power hoses, this will be at much lower level. Therefore, head causing the flow will be high. Okay, at river bed level, we have another turbine. So power capacities are also specified here, and also we have the river water quality requirement. This is schematic of Bhadra Reservoir and its operation, which is actually in Chikmagalur district in Karnataka, India. Now, let us deal with first of all two objectives. These two objectives are in different nature also. First objective is minimize irrigation deficit. Okay, whatever the water that we are releasing for irrigation to the left bank canal, and to the right bank canal in every time period. And the deficit is demand minus release. Okay, so that demand minus release is squared, so that there is positive or negative, it will be weighted. Okay, and like that for every time period, like for 12 time periods. Okay, so squared deviation of irrigation deficits over all the periods over both the left bank canal as well as right bank canal is what we are trying to minimize, and that is one objective function. Next objective function is maximization type. Okay, and here what happens is the hydropower that is to be generated from left bank canal, right bank canal, and from bed level. Okay, and all these are added together for every day, every month. Okay, and like that over 12 months. Okay, that is your other objective function, hydropower maximization. And it is subject to a bunch of constraints like system dynamics, which I have already shown you in the previous example, storage continuity equation, storage bounds, maximum power production limits, irrigation demands, water quality requirements, etc. Okay, they are all listed here. Don't worry about reading all of them, but basically they are all different constraints. The first one is the most important, storage continuity or system dynamics equation. Okay, and as you can notice, this continuity or the storage limits, etc., are to be there for every time period. So if you have 12 periods in a month, okay, there are 12 constraints here. Like this, there are 12 lower limit constraints, 12 upper limit constraints, so 24 constraints here. Okay, like this. See the number of sets: 1, 3, 6, 8, 10, 11. 11 into 12. That many number of constraints are there as far as this problem is concerned. So then what happens? We solve it using EM, MO, PSO. Then, as you can notice from, let us say, generation or the particles, okay, iterations. Okay, when we are at the 50th generation, you know, all these blue color dots, blue color circles that you are seeing here, the solutions are here. Okay. Please note that F1, objective function 1, we are minimizing, square deficit we are minimizing. F2, we are maximizing. So we want the solutions to be somewhere here. That's why the font is like this when compared to the front that you have seen earlier. Okay. Now, this is the beauty of it. If you consider about, there are about 40 particles or 40 members in the generation. Okay. You can see that they are already forming the almost very close to the Pareto optimal front by about 50th generation. And by the time you come to 200th generation, these rhombuses, black rhombuses that you are seeing here, okay, they are very close to the Pareto optimal front. And by the time you come to 500th generation, okay, or 500th iteration, you can notice that the Pareto optimal front is smoothly defined. The main point that you can notice here is that now all the solutions are not just at one location like this. They are distributed over the entire front, and they are not crowded at one location. They are uniformly distributed. Okay, so entire Pareto optimal front is achieved, okay, using this elitist mutated multi-objective particle swarm optimization. Okay, now, you know, if you just take one point here, what does that point indicate? That point indicates that F1 should be this much and F2 should be this much. That means this is the minimized square irrigation deficit, and this is the corresponding hydropower that we have produced, right? But this is over 1 year. But this point itself has the information about how that water is distributed to different powerhouses and different irrigation channels, and how the water is obtained in each time period. Okay, all that one point itself is this entire curve here. I'll just show you here. Okay, this is the entire curve. Okay, in how much period, how much storage that we should maintain in every time period, okay, is available through that one point, because that's a solution. You know, when you solve this problem, what we actually get is the storage in the reservoir in every time period, and release for irrigation, release for power, and everything is available here. So all these variables are used to develop this kind of table or this kind of curve. Okay, how much storage should be maintained. Now what we also did is that this multi-objective optimization, we try to solve it for various inflow scenarios. One, when we have the normal year, that is, the mean monthly flows are occurring. And one, when there is a bad year, that is inflows are about 1 standard deviation or 0.5 times standard deviation lower than the normal flows, and one where we have higher flows. Okay, like this is a drought year and this is a flood year and this is a normal year. So for all these scenarios, we try to run the multi-objective optimization and obtain the solution. Okay, this is for dry season and this is for a normal season and this is for a wet season or wet year. Okay, and this one point that I am showing here itself talks about one complete curve like this. In each period, how much water should be released for what purpose, or what should be the storage that should be maintained. These are called rule curves, is it not? Rule curve basically talks about what should be the storage maintained in the reservoir in every time period. Okay, that's the way we try to get this, and that also what we did is that if we try to give equal priority to hydropower and irrigation, what will be the solution? And if we give irrigation higher priority, what will be the solution? And if we give hydropower higher priority, what is the solution? So between that, we can choose any solution that is available in this curve. Okay, and like that, this is for dry season, this is for normal season, normal year, and this is for wet year. So we can run it for as many number of inflow scenarios as you want. These are for 3 scenarios, but we can do it for any number of scenarios. My point is not about inflow variation, etc. My point is to talk about multi-objective optimization that you can do with lattice mutated particle swarm optimization. Okay, so that is what is done here. And the same logic, you can extend it, and then we can say that, let's say that I have 3 objectives. 3 objectives being, let us say F1 is irrigation deficit, F2 is hydropower, and F3 is water quality. Okay, so you can see F1 is here, F2 is here, and F3 is here. So the Pareto optimal front, it is no longer a curve, but a Pareto optimal front can be developed like this. Okay, and what happens, you can see that there are too many solutions here. What we can do now, we can use our crowding distance operator and also otherwise scaling as neighbor procedure or something like that, and try to come out with filtered optimal solutions. Okay, so this is what we can provide to the decision maker and say that, well, go ahead and pick up any solution depending on what is the priority relatively you are giving to all these 3 objective functions. That's multi-objective operation or multi-objective optimization, which we can achieve through lattice mutated particle swarm optimization. We have also compared this with NSGA2 and found that we are able to reach this Pareto optimal front much faster and also much more diversified than what we normally get with NSGA2. To conclude, multi-objective evolutionary algorithms are easy to adopt and can provide efficient solutions for multi-objective problems. And these algorithms are capable of handling nonlinear objectives, nonlinear constraints, disconnected Pareto fronts. I did not demonstrate, but we, in the paper that I referred to, we have looked at various disconnected Pareto fronts, which we could easily obtain using our algorithm. Non-convex decision space also can be easily modeled. Okay, and MOES can find solutions to extremely complex and high-dimensional real-world applications in reasonable computation time. What I have shown you is still kind of a hypothetical case where we are talking monthly reservoir operation, and for monthly reservoir operation itself, I have shown you that about 11 sets are there. So if you have 12 time periods, 11 into 12 constraints are there. Same reservoir operation problem, single reservoir only, but let us say that we want to do it on a daily basis. What happens? We'll have 11 into 365 number of constraints will be there. And if you want to do it on a fortnightly basis, you'll have that many. Weekly basis, or if you want to do it hourly basis for hydropower generation, you can talk about 11 into 365 into 24 number of constraints to solve for this optimization problem. Problem dimension will increase, but still we should be able to solve it. And that is where I also talked about parallel computing facility could be used, because MOEs are highly adaptable using cluster computing or multi-process systems. Okay, so MAES have high potential for multi-object automation of hydrological as well as water resource problems. Okay, so that's what I want to discuss about. And this is a paper that I mentioned to you. In one paper, one journal called History Open Journal. Okay, this article is an open access article, and you can go through this to understand various other evolutionary algorithms and swarm intelligence based algorithms which are used in various domains of water resource engineering, not necessarily for reservoir operation, but various domains, and how they are adapted and where they found which one to be better. Okay, so that you can find here. And if you talk about multi-object optimization, multi-criteria decision making, you can also refer to this book, which is very useful to do multi-criteria decision making. Thank you. I'm done and I'm willing to take questions. Dr. Vipin or Pratik? Yeah, so I'm done with my presentation, and if there are any questions, I am willing to take. Yeah, sure. Which graph? I don't know. Maybe he's talking about Pareto optimal front. That graph, when we obtain all the solutions, we can as well plot them using Microsoft Excel. And as far as three-dimensional is concerned, we did it using MATLAB.
Then, sir, how to measure function evolution in optimization problem?
Oh, actually, nowadays what happens is, let us say that we are trying to solve it using, we write this code, let us say in C or in MATLAB. While we are running the program, in MATLAB itself, we can state or ask it to identify the number of floating point operations or the number of function evaluations that are taking place over the entire run. So for example, that program has taken about 20 minutes to obtain the solution. In those 20 minutes, how many number of function evaluations it has taken is an output that can be obtained using MATLAB. You can simply insert that command in the MATLAB at the beginning itself. Then it will tell you how many number of function evaluations are taken. But that can also be done through C, and it can also be done through any other system. Another possibility, this is a reverse engineering. Another possibility is that for a given computer, we know how many number of flops or floating point operations it can do per second. Floating point operations per second. That is defined for a given computer depending on its hardware. Means its RAM, its speed, etc. So if we know that, and if we know that it has taken 20 minutes to execute the complete program, so 20 minutes by number of floating points operations per second will tell you, or it will talk about 20 minutes into the number of floating points operations per second of the computer. Then you also know what is the total number of floating point operations. So there are many ways in which you can estimate the number of functional evaluations.
Then, sir, what are the methods we use for calculating environmental flow to maximize the water quality?
Yeah, this is a very difficult issue to be dealt with. Right now, there are some definitions available. What we try to do is that, one possibility, and this is not the only possibility, one possibility is that the BOD level in the entire system from the dam up to the place where it is safe, okay, maybe a few kilometers downstream, we need to know what is the minimum BOD to be maintained. And to maintain that BOD, what is the amount of water that is required? That can be estimated using very simple equations and to estimate, and that is the amount of flow that we have to maintain. So what I am trying to do is using BOD as a measure to talk about the environmental flow requirements. Otherwise, we can also talk about COD. Or sometimes we also know that a particular type of flora or fauna can survive only if the water level is this much, or again in terms of water quality BOD is this much, then we want to maintain that. So environmental flows are always estimated based on what is the minimum requirements that we have downstream, based on the flora, fauna, or unfortunately, which is actually happening in many reservoirs also, is that if any industry is discharging wastewater into the river downstream of the dam, okay, then also it will create water quality issues. So these are the issues based on which we decide environmental flows, and there are some guidelines that are available which you may be able to get them from NIH website, National Institute of Hydrology website.
Sir, can we keep minimization of soil erosion in the catchment and minimization of sedimentation rate in the reservoir as objectives?
Yeah, um, but those two objectives will not necessarily be conflicting with the water utility objectives, because those two objectives will be dictated by the river basin catchment characteristics down upstream of the dam. Okay, so we can think of doing that in such a way. For example, I'm just giving one crazy example. Let us say that you release all the water from the dam in a few hours, then whatever the inflow that is coming in, it will suddenly find a steep slope. Therefore, water will start rushing to the reservoir. That means it will have a huge amount of erosion capability. So you may want to avoid that. Means what? You want to release water from the dam slowly but not very fast. That is simply one hypothetical case. But the bottom line is that typically the two objectives that you are mentioning will have less amount of conflict with the reservoir operation of objectives that we may have. So we can achieve them as objectives not necessarily conflicting with each other.
Sir, in multi-objective optimization, we will get the feasible set of data every time when we execute the code. So, which we need to consider as the reference solution.
Yeah. As I told that f of x star should be less than f of x. So what we are trying to say is that whether that solution that we have taken is, at least with respect to one objective, is the best or not, or is the highest or not. Highest or not, again, what we are trying to say is that if you further want to improve it, okay, one of the constraints will be violated. We don't want that to happen. So we want non-dominant solution. So every iteration, after every iteration, when you get some solution or some solutions, what you do is check whether that solution is a non-dominant solution or not. If it is, keep it. If it is not, put it into the PSO or any other GA and put it to some more mutation, crossover, etc., and try to get a better solution. And that is where I talk about archiving. So if you found one non-dominant solution, don't again mix it with modification of it by crossover, mutation, etc. Keep it as a light member and keep that continued. That's where we talk about archiving. Okay, that's the advantage. That's why you try to hit the optimal solution or multi-objective optimal solution much faster.
If the solution is best for the one objective and other solution is not the that better solution for another objective, can we
Yeah.
consider that as a data set?
Yes, that is considered as one Pareto optimal solution, because that is the best as far as one objective is concerned, and other objective, it is satisfying the constraints but it is not getting the best value. Okay, so that can be considered as one of the Pareto optimal front. In the curve that I have shown you also, that is basically talking about one of the extremes corners of the Pareto optimal front.
So there is one more question from
Mhm.
slide number 16, that
Mhm.
Pareto optimal solution means that value of x for which there is no other x giving a more minimum function value.
Yeah, right.
But sir,
So
except for one such value, for the all the other yellow dots x value are not giving the best minimum function. Then how can they be treated as solution points?
can you repeat the second portion?
Sorry. The question is, except for one such value for all other yellow dots, x value are not giving the best minimum function values. Then how can they be treated as solution points?
Wow. Sorry, maybe it did not. I did not convey it properly. Let me mention to you that I mean, I think you are referring to this particular yellow dot, where function one has the highest value, but function two has the least value. So as far as function 2 is concerned, this is the least value. Therefore, that is the optimal value. But function 1 has very high value, right? So that is only one possible solution. And even if you look at this yellow dot, what is happening here? F1 is F2 is slightly increased, but F, F1 is substantially reduced. So this is also a good solution. And this is also a good solution. Every yellow dot is a very good solution with respect to one of the objectives or with respect to combination of these two objectives. So all the yellow dots are important multi-objective optimal solutions. Yeah.
Participant, if you have any doubt, then you can unmute yourself and ask. I think all the queries have been solved. So we are
Okay.
very thankful for the speaker that he enlightened us with great knowledge of this lecture. Uh, on behalf of organizing team and initiative, we would give our sincere gratitude to Dr. Nagesh Kumar sir for explaining this in this better way. Thank you, sir.
Thank you. It's a pleasure interacting with all of you. And I wish you all the best. And you're almost closing the program. So congratulations for successfully conducting the training program.